First of all, I'll talk about what the GTTM is. The GTTM is a theory of music that was proposed by Hirata and Jakendorf in 1983. These structures are derived by GTTM. We use grouping and metrical structure to derive a time span tree. We started implementing GTTM on computer in 2004. Here is our evolution of GTTM analyzers and applications. Horizontal axis shows the years. Below the timelines are application of the theory. For example, melody, this one is called expectation piano. In expectation piano, we define the level of time span stability. The predicted notes are displayed on a piano reed. The brightness of each note is depend on the level of time span stability, so it can assist the musical novice to play improvisation. So let me show you a video of expectation piano. This figure shows the level of time span stability, and it shows that the expectation piano works well from a musical point of view. Here's another example called melody morphing. And this figure shows the overview of melody morphing. First, we acquire two time span trees of TA and TB from melody A and B. Then we can acquire common information of TA and TB by using meet operator. So we can acquire TC as an intermediate of TA and TA meet TB because the information of TA includes TA meet TB. And at the same way, we can acquire TD. And finally, we can acquire TC join TD as an intermediate of TA and TB by combining the TC and TD. And let me show you a video of application melody morphing method called shake guitar. Shake guitar ranked first in App Store in music field category in Japan and 30th in USA. However, melody morphing method and shake guitar has a problem. That is, it is difficult to add new songs because the input time span are manually edited by musicologists. So our solution to this problem is to develop an automatic analyzer of GTTM. Above the timelines are analyzers that we developed. For example, this one is called ATTA, which consists of grouping structure analyzer, metrical structure analyzer, and time span tree analyzer. Today, I'll talk about metrical structure analyzer. The GTTM have a lot of rules, and this slide shows the example of applying metrical preference rules in ATTA. each rule is applicable where the values are over the threshold. For example, when we configure the threshold like this, MPR4 will apply these 4 positions. And when we configure here, MPR5A will apply these 4 positions, and MPR5B is apply these 10 positions, and these 3 positions will apply MPR5C. And after applying rules, conflict between rules often occur. For example, here MPR5C will apply, and 5A will apply here. And in this case, the conflict occurs between MPR5C and 5A. A solution to this problem is we introduced adjustable parameters that enable to control the strength of each rule. When we change the parameters, the structure will change. After developing ATTA, we developed interactive GTTM analyzer, which is ATTA with manual editor. So we can edit the structure manually like this. And recently we developed the GTTM analyzer based on probabilistic model. Here, this figure shows the melody reduction by GTTM. And this is a melody and its time span tree. And we can obtain a reduced melody by slicing a tree in the middle and omitting notes that are connected to the branch underlying. And if we apply this reduction process in the inverse direction, we can use it as a generation process. By expressing the generation process using a probabilistic model like PCFZ, we can acquire the most likely time span tree. And as a whole, there are 2 types of GTTM analyzer. One is naive implementation of GTTM. The other is with probabilistic model. And the main advantage of using probabilistic model is that it shows high performance than naive implementation. And they have no or few adjustable parameters. In contrast, the performance is lower than that we expected. Maybe the model is bad, and it needs long computing time. Maybe the optimizer is bad. For example, last year we made Sigma GTTM-III, and we prepared 16 nodes of Geon machine. However, it takes 6 weeks for analyze 100 pieces. Our solution to this problem is to introduce deep learning, which enables to make models from data. And optimizers are progress day by day. In order to introduce deep learning for GTTM analyzers, we have to consider these points. The first one is structure with time trees. There are 2 ways for analysis of one level of metrical structure. One is independently estimate whether one bit can be strong bit or weak bit. The other way is estimate at once. By using multitask learning, we can estimate the one level of metrical structure at once. The second one is GTTM rules. A GTTM consists of rules, and a bit that is applied to many rules tend to be strong in metrical. The applied position of metrical preference rule were helpful clues for estimating where one bit can be strong or weak. So the network runs the metrical preference rules as a single task of multitask learning. The learning is progressed by giving rules as a sub-goal of acquiring metrical structure. The third point is hierarchical metrical structure. A hierarchical metrical structure is generated by iterating the choice of next level structure. The next level structure is recursively generated using the previous structure. However, when we use learning with a single standard network of deep learning, it is difficult to run a higher level structure because many network representations are used for running a lot of structure, a lower level structure. Our solution to this problem is we add new hidden layer for run for the next level structure. And next one is large-scale training data. The large-scale data are needed to train a deep layer network, otherwise the model is overfitting. The label is not needed for unsupervised pre-training, so we collected 15,000 pieces of music formatted in Musical X-Men from web pages. We needed label data to supervise fine-tune the network. Although we had 300 pieces with label in the GTTM database, however, the 300 was too small to enable the network to run. So we artificially increased the label data set like this. Final one is long computing time. Our solution to this problem is very simple: to collaborate with Intel. We collaborate with Intel China team, and they optimize the Python mathematical library called Theano. And here's the result. And in pre-training, Intel Hathor EP runs 2.4 times faster than GPGPU. And in fine-tuning, the Hathor EP runs 1.8 times faster than GPGPU. And also, the Hathor EP can run almost 13 times larger data set than GPGPU. You can download the Intel Theano from this URL, github.com/PCS-Theano. And here is a network of the DeepGTTM-II. We use deep belief network for generating the metrical structure. The network had 11 hidden layers with 3,000 units. The input of the network is onset time, offset time, pitch velocity of node sequence, and grouping structure. The output of the network is 7 types of MPRs and 1 level of metrical structure. Individual output had 2 units, such as rules were not applicable and applicable, or with weak and strong bits. And direct running from input to output is impossible. So we made 4 steps. First, unsupervised pre-training was done by starting restrict Boltzmann machine from the input layer to the hidden layer N. And second, supervised fine-tuning was done by backpropagation from metrical preference rules to input layers. Third, supervised fine-tuning was done with label dataset with a level of metrical structure. And finally, if the metrical structure had a next level, add 1 hidden layer and pre-train the hidden layer using the non-label dataset, then repeat 2 and 3. Here's the experimental result. We evaluated the performance of the DeepGTTM-II by using 100 music pieces from the GTTM database, where the remaining 200 pieces were used to train the network. And the result indicate DeepGTTM-II outperformed the previous analysis in the F measure. Now here's the conclusion. we developed metrical structure analyzer called DeepGTTM-II that was based on deep learning. The DeepGTTM-II outperformed the previous analysis. We plan to implement a complete analysis of GTTM by using deep learning. That's it. Thank you very much.